Now that we have a basic understandings of what are the components that we want to use in music and that describe music and of the operations that we can do on these components, on notes and rests and sequences of notes and so on, let's talk about how we can combine all this into something that resembles a composition. And so in this unit, we start work actually through the means of combining these primitives into a coherent musical piece. We'll clearly use the operation we have introduced so far, but we'll do this starting from kind of a strange place. We'll start actually from creating music from processes like randomness or mathematical models, so that we see how we can combine like the complexity of some of these processes into a complexity of a musical performance or musical product. So we'll talk about randomness and random walk and Markov chains that are there are concepts that are very important in the context of statistical mechanics and complexity science. We'll talk about mathematical models and game of life, for instance, or even the easy model as models we can use to process musical information. In harnessing randomness, we have always we have to solve a series of problems. There are true problems even if we are not talking about randomness, but we are trying to map a process into a musical information. That is, we need to map whatever distributions of numbers we have from random generation, for instance, into sound parameters. So notes, rests, durations, octaves, all the attributes that we have been talking about in the past units. Now, randomness itself, and you can try for yourself in the notebook associated with this unit, results in somewhat incoherent musical structures, because there is no correlation between what we generate and the sequence of the notes of rests that come out of the process. And so we can actually look more into stochastic generation of musical processes through random walks or Markov chains. In a correlated stochastic process, past event influence the future events at some level, and so the resulting musical information has a more coherent sense also from the point of view of our perception, because we are the ones that listen to music and we have to make sense of the music that we hear. So let's start from random walk, and you can follow along on the notebook where I actually show you in practice how the generation of the sound happens with all these processes. Random walks are processes that describe a path that consists of succession of random steps on some mathematical space. So if we take, for instance, the space of integers, a random walk is a process that starts from, say, a particular number, 0, and then at each successive steps can either increment by 1 or decrement by 1 that initial number. So we can go from 0 to 1 to 2 to 1 to 2 to 3 to 1 to 0 to -1, for instance. That's a random walk where each step is determined by an equal probability of happening. We can change that probability of moving up or down, so we can have, instead of 50-50, we can have different probabilities. We can change the length of the step, we can go by 2 steps or 3 steps. That means we can, in this way, you already see this, hopefully, that we can use this as a way of incrementing a starting note by intervals. And so to generate a musical sequence of note sequence where the intervals are controlled by a random walk. The next thing that I want to introduce here is the concept of Markov chains as a generalization of a random walk. So a Markov process exhibits a conditional probability where basically the next outcome depends on one or more of the past outcomes. And the classical example of a Markov chain, for instance, is the coin toss process, where for each coin toss you have an equal probability of tossing the next instance of the coin, so heads or tail. And these processes can be summarized using transition tables that are basically matrices of probabilities that, as in this example here in the view graph, you have a 50-50 balanced Markov chain for the coin toss, where head has an equal probability of going to head or tail in the future, and so tail has an equal probability of going head or tail in the distribution. Again, this is a process that we can use to map on musical objects and produce a combination of sounds, a sequence of sounds with specific characteristics. Of course, in a transition table, all the probability have to sum to 1. This is basic probability theory. But the interesting aspect here is that since you are working with different options of chances, you can generate Markov chains that have higher order, for instance, transition probability. So you can have a probability that depends on the history of the sequence, not just by the previous event, but for more events. And it works very well if one can use this to predict or to generate sequences where different outcomes have very different probabilities. And this is something that can be encoded as a musical rule. So you can write a transition table that encodes some of the musical the aspects of music theory that allow you to generate through this process a sequence that makes sense also according to some higher rule. So an example of this that you can find again in the notebook is the example where by a choice of a particular transition matrix, we generate a musical sequence that resembles the rules of the Gregorian chant. And this approach based on Markov chain has been used also in the context of generating chord sequences for tonal music, for instance, for where we have a large amount of information and statistics on what chord follows what chord in a particular sequence, for instance, in classical music, in Western classical music. An example of what I was saying earlier, let's say that we want to generate a chord progression that mimics a particular piece, a chord progression like Mozart would have used in a piano sonata. So what you need to do is you have to take a corpus of all these chords that Mozart uses, and there are databases that one can analyze for that. Calculate probability distributions for chords to follow a particular chord. And so now you are basically building the database that will allow you to define your transition matrix. Define a starting point, your first chord, and then do a random choice with a probability distribution that is weighted against the probability distribution that you observed in the actual data set of those particular chords. And then you repeat this process, and eventually you produce a chord progression. And you can see for this a particularly interesting paper that is linked here in this slide, where this Markov chain generation, musical generation, is described in detail. We can also use different rules or different processes to generate musical information. And I want to discuss here two particular examples that I personally have created. One that is based on the cellular automata, the game of life, devised originally by John Conway in 1970s. And another one that is based on a very famous and important model of statistical physics, that is the Ising model. It's a model that is used to describe the behavior, say, of a magnetic system, to describe magnetism in materials. So let's talk about game of life and then talk about a particular mapping of this information onto sound parameters. So you can see here in the slide an example of an animation of this cellular automaton. The game of life is characterized by a two-dimensional grid of cells, or square objects, each of which can be either live or dead, or populated or unpopulated. And every cell interacts with its 8 neighbors, which are the cells that are horizontally, vertically, or diagonally distributed, adjacent. And depending on the values of the surrounding cells, that central cell changes its status. And the rules are very simple. There are 4 rules in the game of life. They are listed here in this slide. You can read the rules here. Any live cell with fewer than 2 neighbors dies. And this kind of mimics a mechanism of underpopulation. Any live cell with 2 or 3 live neighbors lives, and so lives to the next generation. Any live cell with more than 3 neighbors dies, as in overpopulation. And any dead cell can actually become live if there are exactly 3 live neighbors of it that basically mimic a reproduction act. So we can put all this together, but and kind of think about a mapping of all these parameters into a particular sound. And there are, of course, many different choices. As I showed you earlier, you can map onto individual notes and durations, and we have examples of this in the notebook. But you actually can also map this configuration to sound parameters, as we would do in a digital sound synthesis. We can manipulate sound parameters like the timbre or the harmonic content of a sound using the information that comes from these particular simulations. And these are 2 examples of this game of life synthesis. So you will hear how the individual configurations of these 2 different squares, this different configuration of cells, generate different sounds that changes in time. So the last model that I want to show you is, again, something that I will be mapping to a sound synthesis process, but this time, instead of using the rules of game of life, I use the Ising model for a magnetic system. So the model consists of discrete variables that represent magnetic dipole moments or atomic spins. They can be in 2 states, either up or down. The spins are arranged in a graph, a lattice. They can be 1-dimensional, 2-dimensional, 3-dimensional, and there is an enormous amount of literature on the study of these models and various variations of these models depending on the interactions between the spins and so on. The idea is an idea of minimizing the configurational energy of the system. And to do so, there are very efficient computational techniques that have been developed over decades, the most important of which is the Monte Carlo and Metropolis algorithm, where you probe the energy state of the system by consistently flipping at random spins and recalculate the energy and deciding if that configuration has to be taken in consideration or discarded. I don't want to go in details here. You can see on the slide there are more information about this, and you'll find a lot of it online, but just by Googling the Ising model. So the mapping here is going to be the same as the mapping of the game of life. The only difference here is that I map spins instead of the individual configurations of the game of life game. And so again, I could map the spins to musical parameters such as notes, durations, or volume, or dynamics, or all those kind of things, or map the spins directly to sound parameters, again, doing digital sound synthesis. And this is the result.